Welcome back to Brainwaves. Today we're going to unravel the mysterious concept of spontaneous symmetry breaking. It's one of the key ideas in particle physics, but it sounds way more complicated than it is. By the end of this video, you'll not only understand it, but you'll also see how this process is at the heart of everything, from the particles that make up your body to the forces that govern the entire universe. What exactly is symmetry? Before we can talk about symmetry breaking, let's first understand what we mean by symmetry. In everyday life, symmetry usually means something is balanced or looks the same in all directions. Imagine standing in front of a mirror. If the reflection looks the same as the original, we say there's symmetry. Similarly, in physics, symmetry means that the laws of physics don't change if you look at a system in different ways. For example, if you rotate a perfect circle, it still looks the same no matter how you turn it. That's rotational symmetry. If you flip an equation describing a particle interaction in space or time, and it still works out the same, that's symmetry too. Now, in the early universe, things were very symmetrical. At the start of the Big Bang, all the forces, gravity, electromagnetism, and the nuclear forces, may have been unified, acting as one, with particles behaving the same way. Everything was in perfect balance, but here's the catch. The universe we live in today is not symmetrical in that way anymore. The different forces act independently, particles have different masses, and the universe is a messier, more interesting place. This leads us to the idea of symmetry breaking. Symmetry breaking, a step-by-step process. Let's get into it by using a more detailed analogy. Imagine you're sitting at a perfectly round dinner table, and you're about to have a meal with your friends. In the middle of the table is a bowl of bread, placed exactly at the center. At this point, the table has symmetry because it looks exactly the same no matter where you sit. But now, someone reaches for the bread. As soon as someone grabs a piece from one side, the symmetry of the situation is broken. Now the table is no longer symmetrical because the bread is no longer in the center. In physics, this is what happens when a system that could stay perfectly symmetrical chooses a specific outcome, breaking the symmetry. In spontaneous symmetry breaking, the universe or a particular system starts in a balanced state, but something pushes it into an uneven, less symmetrical state. The kicker is that this breaking happens spontaneously, without an obvious external force acting on it. The system itself decides to favor one state over another. The Higgs field and particle mass, a symmetry-breaking superstar. Now, how does this apply to particle physics? Let's talk about the Higgs field, which is central to this concept. The Higgs field is an energy field that fills the entire universe, but it wasn't always in its current state. In the beginning, it was symmetrical, like that ball balanced perfectly on top of a hill. Everything in the universe would have had no mass, particles would have zipped around at the speed of light, and there would be no structure to anything. But just like the ball that eventually rolls down the hill, the Higgs field eventually broke that symmetry. Instead of staying in a high-energy symmetrical state, the Higgs field chose a particular direction or energy level, and this breaking is what gave particles their mass. To understand this better, think about the potential energy landscape of the Higgs field. Visualize a wine bottle lying on its side. The very bottom of the bottle is a dip, where the energy is lowest. The perfectly symmetrical point is at the top of the bottle's neck, but this position is unstable. If you place a marble on top, it won't stay there. It'll roll down the sides. And once it rolls down, the marble chooses a spot at the lowest point of energy. Even though the bottle's shape is symmetrical, the marble picking a spot at the bottom breaks the symmetry. In particle physics, when the Higgs field rolled into its low-energy state, it picked certain properties for particles. Some particles, like the electron, interact strongly with the Higgs field and get a lot of mass, while others, like the photon, light particle, don't interact with it at all and remain massless. Without this spontaneous symmetry breaking, particles like the electron wouldn't have mass, and atoms couldn't form, which means matter, and everything around us wouldn't exist. How spontaneous symmetry breaking created the universe's structure. Here's where it gets even more mind-blowing. This process didn't just affect particle masses. Symmetry breaking is the reason our universe has structure at all. In the early moments after the Big Bang, everything was hot and chaotic, and all the forces, gravity, electromagnetism, and the strong and weak nuclear forces, might have been unified into one superforce. But as the universe cooled, the forces started to separate, breaking their symmetry. Think about it like water freezing into ice. When water is hot, the molecules are bouncing around everywhere, completely disorganized. But as it cools and freezes, the water molecules choose an arrangement, forming a more structured, solid pattern. This is essentially what happened with the universe's forces as the temperature dropped. The symmetry broke, and the four fundamental forces of nature as we know them today separated from each other. One of the most important consequences of this is that it allowed matter to form. The symmetry breaking that separated the forces is what gave rise to particles and atoms. Without it, the universe would still be a hot, formless soup of energy. No stars, no planets, no life. Symmetry breaking and the mystery of matter and antimatter. Here's another twist. Symmetry breaking might also explain one of the greatest mysteries of the universe: why there's more matter than antimatter. At the beginning of the universe, there should have been equal amounts of both, but as we look around, the universe is dominated by matter. Scientists believe that some form of spontaneous symmetry breaking early in the universe's history caused a small imbalance, just enough matter to survive after matter and antimatter annihilated each other. This tiny asymmetry, about one extra matter particle for every billion particles of antimatter, was all that was left over to form the galaxies, stars, planets, and everything you see around you. Conclusion: why symmetry breaking is so fundamental. Spontaneous symmetry breaking isn't just a complex idea tucked away in particle physics textbooks. It's a cosmic event that shaped the universe itself. From giving particles their mass to explaining why the universe has structure and why we're here today, symmetry breaking is a key that unlocks so many mysteries. The next time you look up at the stars or think about how everything is made up of tiny particles, remember that this is all possible because of a tiny, spontaneous nudge that broke the perfect symmetry of the early universe. Thanks for watching Brainwaves, where we break down the universe's most incredible phenomena. Make sure to subscribe and hit that bell icon for more deep dives into the fascinating world of physics. Until next time, keep those brainwaves buzzing.